When you combine many independent disturbances or measurements into a single aggregate output, their behavior stabilizes into a predictable shape. This is the operational intuition behind system averaging. No matter what individual fluctuations look like, their collective effect converges toward a well-defined distribution. This is not magic. It emerges from the mathematics of independence and superposition. The central limit theorem formalizes this. The average of many independent, identically distributed random variables approaches a Gaussian distribution as the sample size grows. This holds regardless of the original distribution shape. The mechanism is algebraic. The characteristic function of the average decays to that of a normal distribution under specific conditions. For engineering systems, this means system-level outputs develop Gaussian behavior even when component errors are non-Gaussian. This is the theorem's power. But convergence speed varies. Symmetric distributions settle into Gaussian shape quickly. Skewed distributions require larger sample sizes to show clear Gaussian structure. The rate of approach depends on the third central moment, the skewness of the source distribution. In a control system, this means fast aggregation of symmetric noise gives you reliable Gaussian behavior early. Asymmetric perturbations demand patience or larger measurements before you can trust the central limit approximation. Heavy-tailed distributions expose a critical failure mode. When extreme values occur with non-negligible probability, such as in network latencies, financial shocks, or cascading failures, those outliers dominate the aggregate. A single catastrophic event can skew the average far beyond what a Gaussian model predicts. The central limit theorem no longer applies in this regime. For complex systems with rare but severe disturbances, relying on CLT-derived confidence intervals is dangerous. You lose the guarantee of convergence to normality. The theorem demands finite variance as its foundation. Without this condition, averaging breaks down algebraically. Infinite variance, such as in power law or Pareto distributed systems, means the contribution of extreme events never stabilizes. The average itself exhibits infinite variability across different samples. In reliability engineering, this is the distinction between manageable noise and pathological instability. You must verify that your system's source distribution has bounded second moment before treating aggregates as Gaussian. The central limit theorem is powerful, but not universal. It guarantees convergence shape only when independence, identical distribution, and finite variance hold. In real systems, these are assumptions, not facts. Correlated failures, non-stationary sources, and heavy-tailed events all violate the premises. When designing control architectures or reliability systems, treat the CLT as a design heuristic, not a proof. Validate its applicability in your specific domain. The shape it predicts is only as reliable as the conditions you enforce.